In this work, we introduce UniPixie, a framework for unified and probabilistic three-dimensional physics learning via flow matching. Modern three-dimensional reconstruction methods can recover detailed geometry and appearance from images. However, they remain blind to physics. When an object is pushed, dropped, or squeezed, its behavior depends on invisible physical properties, such as stiffness, density, and material type. The key challenge is ambiguity. The same looking object can be soft, stiff, or anywhere in between. A deterministic model that predicts only one material value cannot capture this range of plausible physical realities. UniPixie addresses this challenge with three main contributions. First, we reframe physics prediction as generative physics. Instead of predicting a single point estimate, UniPixie learns a controllable, soft-to-stiff spectrum of physically plausible material properties. Second, we introduce Pixie Multiverse, a dataset with material property range annotations. This allows the model to learn not just one material label, but a continuous range of possible physical behaviors. Third, we propose a unified, multi-solver architecture. From the same visual input, UniPixie generates simulation-ready parameters for multiple physics engines, including MPM, LBS, and spring mass systems. Let us first look at the dataset. Pixie Multiverse starts from high-quality three-dimensional assets. For each object, we use vision language models to propose semantic parts, material ranges, and physical constraints. These annotations are then checked with part segmentation, boundary simulations at the soft and stiff endpoints, and human verification. This gives us supervision for learning a continuous physical spectrum rather than a single deterministic material value. Now let us move to the model. Given multi-view visual input, UniPixie first extracts visual features and lifts them into a three-dimensional voxel grid. A shared encoder then converts this grid into a compact set of physics-aware latent tokens. These latent tokens represent the object's geometry, appearance, and possible physical behavior. A conditional flow matching decoder then generates physical property fields conditioned on a single control parameter, alpha. The same latent representation is also used for multi-solver decoding. Instead of being tied to a single simulation backend, UniPixie uses specialized decoders to produce parameters for three different physics solvers. For MPM, it predicts volumetric material fields such as Young's modulus, density, Poisson's ratio, and material class. For LBS, it produces parameters for reduced order deformation. For spring mass systems, it predicts anchor stiffness and global softness. This makes the output portable across different simulation paradigms. We now evaluate whether this generative formulation improves physical prediction. Compared with deterministic baselines such as Nerf to Physics, PUGS, and Pixie, UniPixie achieves more accurate continuous property prediction. In particular, for Young's modulus, the error is reduced from 0.0205 with Pixie to 0.0091 with UniPixie. This is more than a 50% reduction over the strongest deterministic baseline. This improvement also leads to more plausible simulations. For flexible plants, baseline methods often produce overly rigid or rubber-like motion, while UniPixie generates compliant deformation. For a stuffed toy, material misclassification can cause a baseline simulation to collapse, but UniPixie preserves structural integrity and produces the expected elastic behavior. For a rigid metal object, UniPixie correctly predicts high stiffness and avoids unrealistic soft warping. Next, we evaluate multi-solver generalization. A single UniPixie model can drive MPM, LBS, and spring mass systems. It achieves competitive or better reconstruction quality compared with solver-specific baselines, while avoiding slow test time optimization. This is important for efficiency. Optimization-based methods, such as vid2sim or spring Gauss, can take minutes or even hours for a single object. UniPixie generates simulation-ready parameters for all three solvers in about 21 seconds. Finally, let us look at controllability. With the same rubber duck input, changing alpha produces clearly different physical behaviors. At low alpha, the duck behaves like a soft object and squashes upon impact. At high alpha, it behaves like a stiff object and largely preserves its shape. This soft to stiff control is consistent across MPM, LBS, and spring mass simulations. In summary, UniPixie turns physics from vision into a controllable generative modeling problem. With Pixie Multiverse, it learns material property ranges rather than single labels. With a unified multi-solver architecture, it produces simulation-ready parameters for diverse physics engines. As a result, UniPixie bridges the gap between static visual perception and dynamic physical reality. Thank you for watching.